Hello guys, I'm back. If you need to learn PSV calculations for supercritical fluids, stay with me until the end of this video because I will teach you how to do hand calculations and also how to use the Aspen Hysys to define the required flow and also the orifice size of your PSV for supercritical fluids. My name is Jeferson Costa and I teach students, graduates, and engineers how to work with chemical process engineering and plant design. One of the tasks of a chemical process engineer that works with plant design is to verify and identify scenarios that can lead to unsafe conditions in an industrial plant. We perform the heat and material balance, and with the results of the heat and material balance, we develop process flow diagrams and piping and instrumentation diagrams. And is in the piping instrumentation diagram that we add the pressure safety device elements to avoid, mitigate, or prevent the unsafe conditions that can happen in a process. But to be able to identify what kind of scenario can lead to an unsafe condition, the chemical process engineer must understand what are the source of this unsafety. It can be high pressure, high temperature, low temperature. And one of the ways that can help you to understand this kind of possible scenario that can happen to your process is the literature, like books, but also the standards. So the first thing that you must do when you are dealing with chemical process engineering and plant design is be familiar with the main standards that are related to the relief and the pressurization of systems. The main one for sure is the API 520 Part 1 and Part 2, and also the API 521. With the basic set, you will be familiar with a lot of information to do the sizing of orifice for a pressure relief device and also how to define the amount of flow or the required flow for each scenario that can happen in your industrial plant. Talking about the API 520 Part 1, it is related to the sizing and selection of the orifice of your pressure safety device. And the Part 2, you will find recommendations for installation of the PSV and others process safety devices. And it is in the API 521 that talks about pressure relieving and the pressure system that you find the procedures to estimate or to calculate the required flow to the definition of a pressure safety device. So based on that, the first thing that you should do is get familiar with the API 521 because it is in this standard that you will find a step-by-step on how to do the hand calculations for supercritical fluids. We will review it with some comments, but to do the calculations for the orifice of your PSV, you need to be familiar with the API 520 because there you will find the equations to calculate the orifice. If you don't have access to API standards, an excellent source of information is the Pressure Relief Valve Engineering Handbook from Amazon. In this handbook, you will find a summarization of the API standards and you'll be able to get familiar on how to do the calculations for the orifice of a pressure relief device. Although it doesn't talk about supercritical fluids, in any case, I strongly recommend you to get in touch with this handbook. You can find it from the internet, in the Amazon website, or if you prefer, you can download it from my Telegram channel in process. That said, let's see what are the typical scenarios for pressure relief device calculations. Safety scenarios for pressure relief device calculations is any scenario that can lead to an overpressurization of your system. In API 521, you find on Table 1 17 scenarios listed by the standard, and in the Aspen Hysys, in the safety analysis, you also have a summarization of them. So here you can see that, for instance, fire is a scenario where you can have overpressurization of your system, because if you keep adding heat to a vessel, the fluid that's inside the vessel will expand, and with that will increase the pressure until it reach the maximum allowable working pressure of the equipment, or you relieve the amount of fluid that is inside that to prevent the overpressurization. Another case of, or another scenario of overpressurization is a control valve failure. Most often, when we are dealing with the pressure control, you want to decrease high pressure for a low pressure, and you need to consider the scenario of having this control valve full open. So what happens if you have a high pressure upstream of your control valve and it goes to downstream of your control valve? Most often, the downstream process is not able to reach the same amount of pressure that the upstream of your control valve, and because of that, you need to consider pressure relief devices to prevent the rupture of your system. Imagine that you need to compress a fluid to a process, and in the aftercooler it is a sharing tube heat exchanger, and you use a cooling water system with a pressure around 3.5 bar G. If for any reason the heat exchanger, the tube erupts, or if you get a hole in the tube because corrosion, for instance, you need to verify what happens when the fluid at the high pressure goes to the side of the lower pressure of your system. So these are examples of scenarios for pressure relief device calculations. There are many others, and what's important to understand in terms of critical fluids is that a supercritical fluid release is not a scenario, it is a condition of a process. And to understand better that, you need to know what are supercritical fluids. In a few words, supercritical fluids are fluids that the condition of pressure and temperature are above its critical point. Here in my screen, you can see a pressure temperature chart of the N-butane, and the blue line represents the equilibrium phase between the liquids. At this side, I have low temperature and I can have high pressure, and the gas phase or the vapor phase, where I have high temperature and I can have low pressure. But if I increase the temperature and I increase the pressure, I will get my equilibrium curve until I reach the yellow point. The yellow point, I have the critical point, and from above this point, my fluid is not a liquid, it's not a gas, it can be something between both of them and with some specific properties. So to verify what is the critical point of a fluid, if you are using the Aspen Hysys, you just need to go to table of the attachment envelope and verify the lowest or the latest pressure and also temperature. So this pair of information is the critical pressure and the critical temperature of the fluid. Verify that in normal operating conditions, for instance, 90 Fahrenheit and 44 psi, the N-butane will be a liquid, but if I increase the temperature and the pressure, it will reach the critical point. And why it is important to us? It is important to us because although our fluid can be a liquid or a vapor in normal operating conditions, if we have a fire case scenario, we can reach the supercritical condition of our fluid. Imagine that we have a liquid inside a vessel, and the set point of the pressure relief device for this vessel is above the critical point of the fluid. When it happens in a fire case condition, we will have the addition of heat to the vessel, and because the liquid is in a confined space, the addition of heat will lead to the increase of temperature and also the increase of pressure, because there is no way that the fluid can be relieved until the set point of the pressure relief device. So in this case, the fluid will get the equilibrium line, increasing the pressure and temperature until it reaches the critical pressure and critical temperature point. From this point here, with the addition of heat, the fluid will keep increasing its pressure and temperature in a constant specific volume, because the mass of fluid is the same, the volume of the space is the same until it reaches the pressure relief set point. In this point, we will have the opening of the pressure relief device, and the fluid will be released in a constant entropy. So in this way, we'll keep releasing the fluid until the vessel is empty or the source of heat is ended. This theory here is very important when you are doing the rigorous calculations of pressure relief devices for supercritical fluids. There are two ways to do pressure relief devices calculations for supercritical fluids. One of them is using the API 521 standard equation, and another one is using the rigorous mode. And we'll see both of them in this video. Let's start with the API 521 calculations. You'll find the calculations for pressure relief devices for supercritical fluids in the section Heat Absorption Equations for vessel containing only gases, vapor, or supercritical fluids. There are some equations here. It starts with the equation 9, but to solve the equation 9, you need to have the area exposed to fire, so it's a function of the geometry of your vessel. You need to have the set point of your case, and the set point considers the allowable overpressure of your system. So when we are talking about fire case, we have an allowance of 21%, and it depends on the F dash. But the F dash goes to another equation where we need to calculate the C, the KD. KD is a function of your pressure relief device, and we have also the C9, that is a constant. And you need to define what is the temperature, allowable temperature for the wall of your vessel, and the release temperature. And here we have the first issue, because to define the temperature release, or the temperature at the upstream relief pressure, we need to use the calculation or the equation 12 that uses the relation of the ideal gas. So if I have a liquid at my normal operating conditions, I am not able to just get the normal operating conditions of a liquid and add this to this equation, because this equation is for ideal gases. So I need to find a way to convert or to do an estimation of my temperature release before I am able to apply this equation. And we'll see with the example how to do that. Moreover, to find the value of K, that is Cp divided by Cv, I need to consider it at the pressure relief setting or at the set point of my pressure relief device, and also the temperature of release. That depends on this equation. So the procedure for starting the calculations for the pressure relief device, the calculation of the orifice of your pressure relief device, is first solve equation 12. After that, solve equation 11. With equation 11, solve equation 10. And with equation 10, solve the equation 9. With this, you will find the orifice area of your pressure relief device. Once you find that, you are able to calculate the required load for your pressure relief device. And that will depend on the F- calculation. If it is above a certain value, you will use this equation here, 13, or if it is below certain value, you will use the equation 14. So with that, let's see a case study and start with the calculations. For our case study, we have here a vessel that is filled with N-butane. So in normal operating conditions, 44 psi and 90 Fahrenheit degrees, it is a liquid. But because of the fire case, we have heat adding for this vessel that is insulated, and it influences the amount of heat that we add to the vessel, but do not influences the standard calculations for the API 521. We have the geometry of this vessel and the conditions in terms of PSV set point, that is 800 psi with 21% allowable overpressure. So to define the pressure safety device relief pressure, we need to convert the manometric pressure plus the allowable overpressure to absolute pressure. In this way, we have 1.21 multiplied by 800 plus 14.7. This 14.7 refers to the barometric pressure. So if you are in a higher place, the barometric pressure will be lower than 14.7. And if you are at sea level, you can consider the 14.7. So based on that, we have the relief pressure of our system. And in this case, the author, for some reason, I don't know the reason, set the temperature of the fluid as a starting point of 815 Rankine. So based on the PSV set point and the temperature of the fluid, we can see that the conditions is above the critical point of the N-butane, because the critical pressure is 550 psi and the critical temperature is 765 Rankine. So in this way, when we have the release of this pressure relief device, we will have a release of a supercritical fluid. But as I told you, we'll do the first calculations based on the API 521 standard. And in the standard equation, or in the standards calculation, some of the information that we have here will not apply. So the first step for doing the calculation according to API 521 is to do the calculation of the exposed area of your vessel. So as we have an elliptical heads vessel here, we'll use this equation here. So based on this equation and the information of diameter and the age of the vessel, I reach an exposed area of 304.23 feet square. So this information I add to my spreadsheet. The second step is to define the relief temperature of your case, or at least estimate the relief temperature of your case. Based on this equation, you can apply it only if your gas, if your component, or if your fluid is a gas, or eventually if it is in the supercritical condition. If in the normal operating conditions your fluid is a liquid, you cannot apply this equation straight. In any case, according to the paper, we already have the temperature above the critical point and we have the set pressure above the critical point. So in this case, what I did to define the T1, that is the relief temperature, was to use the references that I have. So what I have as set point pressure or release pressure is 982.7 psi. My normal pressure is also the set point because it's the reference that I have in the paper. And my normal temperature, it was already added also or informed by the paper, that is 815 Rankine. So based on that, doing these calculations, as I have the pressure divided by the semi-pressure, I have a 1. So in this case, for the API calculation, my release temperature will be the same of the paper. In real life, you will not have this information available to you. So how can you estimate the relief temperature if you have your fluid as liquid conditions in normal operation? To do that, let's get the support of a process simulation software like Aspen Hysys. But first, let's review the fundamentals. So I have told you that in the initial condition, if you have liquid, it will be in equilibrium with the vapor phase, and as we add heat to the vessel, the fluid will increase its temperature and also its pressure until it reaches the critical point. From the critical point to the pressure relief device set point, we will have a line of constant specific volume, and the mass density will also be constant because the specific volume is the opposite of the specific mass. So based on that, as I have a specific volume of the fluid and I have the pressure condition of the release, I can estimate or I can find what is the temperature that matches these two information. So to do that, let's go to the Aspen Hysys. So here I have my stream set according to the information of the paper in terms of temperature and pressure. And with this information, I can go to properties and look for the CPCV. That is here and also in the table here to let my life easier. And now, considering that we don't have the information of the release temperature, what we need to do is to verify what is the conditions of the critical point, critical temperature and critical pressure. On those conditions, verify what is the mass density of the fluid, and after that, set the mass density of the fluid and adjust the temperature to get the same result. So one step after another. First thing is to find what is the critical point of this stream. We already have that, but if you don't know how to find it, you just need to go to Attachment, go to Analysis, Create, Envelope, Add, and with that, you will choose your stream and click on OK. When you do that, you will open this window with Envelope, and if you go to Performance, you can see the last values. They are the critical points, or in the Design tab, you are able also to see the critical temperature and critical pressure. What I will do with this information? With this information, I will return to my worksheet and I will adjust the temperature and the pressure. So in this case, I will get the temperature and add to my stream, and I will get the pressure and add to my stream also. The main objective of this procedure is go to the properties and find the mass density. That is already here. But if we go to properties, you will verify the mass density, that is 10.71. Based on this information, now I will return to my conditions. I want to verify what is the temperature where my density is 10.7147. That is the mass density with the decimals. So based on that, I will run my adjust to verify what is the temperature that matches with the pressure. So my target is mass density and my adjusted variable is temperature. So I will just uncheck the ignore, and to run my adjust, I need to set a handle value of temperature, for instance 550. With that, the Aspen Hysys did the calculation, the adjust converted, as you can see, and my temperature of reference can be the 873.6 Rankine. As this temperature is different from the temperature considered in the paper, of course that the CP and CV will also be different. But do not matter if you don't have any other information to be added to your API 521 calculations. This is the best reference that you can have to do your job. For a while, I will not use this information. I will keep with the informations of the paper. So as we have the temperature release definition here, in this case 815 Rankine, I am able with the pressure relief, temperature relief, find the CPCV, and I need to add it to my spreadsheet. And with the K and with the temp, that is a constant, added here, I am able to do the calculations of C, that in this case is 393. So what I just did here in my spreadsheet was let this easier to do the calculations. I get the C temp and I splitted the square root in different topics or in different parts. But in the end, what matters for me is the final result that I will use in the equation 10. To calculate the equation 10, I need to have the C9, that is a constant, is already here. I need to have the KD, that is information for the supplier, but the API recommends an initial value to be used. I need the information of C that was just calculated. I need the information of the release temperature that was already considered from the paper, and I need the temperature of the wall of your vessel. And this is the maximum allowable temperature that your material can reach before it fails. The API highlights that usually for carbon steel, the T-wall will be 1100 Fahrenheit. So in this way, I added this information to the spreadsheet. So with all of this information, it's possible to calculate the F dash. So the F dash is this one using the information that I have told to you. And once again, I splitted my equation to let easier for the calculations results. So based on that, I have the F dash and I am able to do the calculation of the equation 9. So is in the equation 9 that effectively will do the calculation of the orifice. That depends on the F dash, we already calculated that, depends on the area exposed to the fire, and depends on the relief pressure. So based on all of these informations that are available here, we are able to get the orifice in inches. So in this case, I have the orifice in inches square. Once I have the orifice and I have the F dash, I can do the calculation for the relief loads for this pressure relief device. So to do that, we need to go to another equation that will consider a value if we have the F dash below the 0.01 or above 0.01. So in this case, we'll use the equation 13 and 14, but as I have my F dash as 0.0182, my equation of consideration will be this one here that represents the equation 13. So in fact, I will use this equation to do the calculation of the required relief of my pressure safety device. That will do to me, in this case, around 17,811 pounds per hour of fluid. This way, with the information of the orifice and the information of the required relief load, if you got to this point, your job is finished. Your job is over. You are able to fill the specification datasheet for the pressure relief device, a PSV most often. But there are a discussion that this standard calculation of the API 521 leads to a Orifice much bigger than it could be if rigorous modes calculations are performed. So let's verify what happens if we do the rigorous modes calculation. The rigorous calculation for sizing relief valves for supercritical fluids was first published by Ryan Kirk. In this paper, he addressed a methodology to base it on the heating added to the fluid, and with the properties of the fluid, it is possible to calculate the relief load, the heat flux, and based on that, do the calculations for the orifice. He has shown in his paper that the maximum orifice or the orifice to be chosen, it's not necessarily when we have the maximum mass relief rate or the maximum volumetric relief rate. In his procedure, we need to do an iterative calculation to find the required area of the pressure relief device. So to do that, first we need to assemble relief case information. So we need to have the basis conditions for our evaluation. We need to select proper method and assembly data, and it is in this point that the calculations proposed by Ryan is very tough for us, because he uses equation of states and tables from handbooks to do the calculations of the fluid, and that for sure gets a lot of time. So based on that, some years later, another author suggested a similar procedure to perform the same calculations, and we will verify that also. But just to get at the original one, we need to do a number of iterations, considering first the calculation of the heat input, and at this point it will be very important the information of insolation. So as you have seen in the standard API 521 calculations, there is no considerations for the heat input. After that, based on the heat input and in the delta T added to your case, you will do the calculations related to some properties of the fluid, like the enthalpy, the liquid density, the entropy, and we will do the calculations of the differences between the current interaction and the previous interaction. With that, we will be able to calculate the volume flow of the fluid and also the mass flow of the fluid. And considering that in the relief conditions, we will have a shocked condition that leads to an isentropic release, we will be able to calculate the mass flux of the system based on isentropic conditions. And with the mass flux and the mass rate and also some other constant, we are able to do the calculation of the orifice, add that to a table, and return with the iteration until we get the maximum calculation of the orifice area. As I told you, these calculations can be tough because are based on the select proper methods. Some years later, from Ryan's work, Richard Duane proposed a rigorous methodology for doing calculations for the designing of pressure safety valves in supercritical servers. In summary, Richard uses as basis for his paper the work developed by Ryan. But he, instead of using the equation of states to define the properties of the fluid, Richard recommends the use of a process simulation software. Richard's chart is very similar to Ryan's chart, but what is interesting in Richard's paper is that he shows how to get the calculations, how to do the calculations based on the normal operating conditions of the fluid. In this case, he gets the same example, N-butane in a vessel, and he shows how to get the fluid as a liquid condition to the supercritical condition, as I have shown to you during this video. So to follow his procedure, we need to have information related to the vessel, for the system related to the back pressure of the system, and also the critical information or the critical properties of your fluids. In fact, you need to know the properties of your fluids. Based on that, you need to do the heat transfer calculation for the system, and it depends on if exists or not a firefight system available. And the first point of the iterations is the relieving pressure and the critical volume of your fluid. So based on that, record the enthalpy, the entropy, and the CPCV, and increment the iterations by the addition of 10 Fahrenheit to each iteration. The pressure, release pressure will be constant, but the temperature will increase. So for each new temperature, you'll find information of the specific volume, enthalpy, entropy, and CPCV. And he recommends at least 5 steps or 5 iterations. Once you fill your table with this information, it's time to perform the calculations. So the first thing is to verify if the condition of a release is choked or not choked. Most often, as the set point of the pressure relief device is very high, the conditions of a release will be choked. And that means that the flow through the orifice will be sonic. And consider that it will be sonic with a constant entropy and the pressure as the choked pressure, we need to find what is the choked temperature. And with the choked temperature, we'll do the recording of the specific volume and also the CPCV. With that, we calculate the fluid velocity through the orifice as a sonic velocity based on this equation, and we calculate the mass flux through the orifice for the choked condition, and that is a very important point. Because here, the mass flux is limited by the choked condition. So that's why we need to use the properties of the fluid based on the choked condition and not in the release conditions. That's done based on the heat input and also the delta specific volume divided by the delta enthalpy. It's possible to calculate the fluid volumetric flow, and with the fluid volumetric flow and the specific volume of the fluid, it's possible to calculate the mass flow of the system. And with the mass flow of the system and with the mass flux and the others constant, using a conversion factor of 0.04 to convert feet square to inch square, it's possible to do the calculation of the orifice. Verify that this calculation here for the mass flow is not correct. You need to fix that, and we'll see in the spreadsheet. So with this, you will have a series of orifice calculations, and you need to verify what is the biggest one. Important to mention that the Aspen Hysys on safety analysis perform the supercritical calculations based on Ryan's procedure, and the API 521 already recognizes this procedure as an alternative procedure that can be used to define the orifice and also the flow calculation. So you can use the standard API 521 calculation to define your pressure relief device, but you can also use this alternative method based on Ryan's procedure and upgraded by Richard. So here what we have in terms of Richard procedure. First thing first, we need to have the information of the fire case and the information related to our vessel. So based on the information of our vessel, we are able to calculate the exposed area. One difference between the Richard example or the Richard paper and the Ryan's paper is that they consider different approaches for the vessel. Ryan's considered that the vessel was insulated, so because of that, the F factor was 0.3, while Richard considered that it was a bare vessel and the F was 1. I will use Ryan's information just to let easier to you verify the differences in the calculation and how close we are able to get to the results, comparing Ryan's calculation and also the Aspen Hysys calculation. And I will not use Richard's results because there are some issues in the table results that he shared in the paper. So first thing first, once you have your fluid, you need to find the information related to critical point. So the critical temperature and critical pressure. With these points here, you are able to verify what is the mass density at the critical conditions and do the calculation of the specific volume of critical conditions. According to the Richard's paper, what you need to do now is set your process simulation in order that you get the same mass density at the relieving pressure. So based on that, we do the calculation of the temperature. So this is the first point of the Richard's procedure. Once I have the new temperature and the relief pressure, the specific volume will be the same, but the information of enthalpy, entropy, and CP/CV will be according to this condition. So based on that, I am able to do the calculation of the choked pressure using the pressure, relief pressure, and the CP/CV. And considering that at choked pressure, I have constant entropy, I will get this information of choked pressure, add to my table, and set the Aspen Hysys, for instance, or other process simulation software to reach the pair of pressure and entropy to find the new temperature. Here I have a second adjust object to do the variation of the temperature to match my mass entropy. So for each pair of information, I will find the new temperature, and with the new temperature, I will get the properties of the fluid at that point. With that, I find the new mass density, calculate the new specific volume, and I also register the new CP/CV. Because for the orifice velocity calculation, I need to use the choked conditions that will get as input. The new CP/CV will get the temperature, and this temperature must be absolute temperature, the molar weight of your component or of your fluid, the constant of gases, and also the constant of gravity. So based on that, we perform the calculation of the velocity of the orifice. That will be used to do the calculation of the mass flux. So I have here that the orifice velocity divided by the specific volume at choked condition will lead to my mass flux at choked condition. After that, I calculate the volume flow based on the differences between my specific volume and my enthalpy multiplied by my heat rate. And finally, I do the calculation of the mass flow based on the volume flow divided by my specific volume at the release conditions. That is very important because now you will not use the calculation based on the choked condition, but at the relief conditions. With mass flow and mass flux, I am able to do the calculation of the orifice that will get into account the KD, KB, and KC. So for first iteration, I will do this procedure and I will have my table with the calculated area or the orifice for each case. and I will choose the case or the relief conditions that leads me to the highest Orifice calculation. That in this case is the 404 Fahrenheit degrees at pressure relief conditions. So my mass flow will be 4,595 pounds per hour. If we go to Ryan's paper, we can see that the relief temperature considered by him is very close to the considered or to calculated by the Richard procedure. We have here 857 Rankine, that represents 397 Fahrenheit. In our spreadsheet, we have 404 Fahrenheit of temperature. So they are very, very close, and the results is very, very close also. If we go to Aspen Hysys and set the operation conditions of the fluid, that is 90 Fahrenheit and 44 psi, so you can see that it is a liquid, and we perform the safety analysis calculation. At the first sight, it seems that the calculation is very far from what we have considered according to the Richard and also Ryan's method. But there are a trick here. If you go to Edit Flash Table, you verify that the iteration made by the Aspen Hysys here is 10 iteration. So what I will do here is to increase this interaction to 100. With that, now we have a temperature differences of 10 Fahrenheit or almost 10 Fahrenheit, that's close to the one that we used to the calculations. If I close this window and I adjust the environment factor and the additional area to 0, we get the same exposed area, and set the drainage and firefighting for present, we get basically the same results that we have in the paper and in the spreadsheet. Verify that I can let the Aspen Hysys suggest the orifice size for my fluid based on the API standard, but although I have a slight differences between the calculations, in fact, the smallest size for the orifice is 0.1. So in any one of these calculations, I will get the same orifice result. So now, as a last verification, let's consider Richard scenario that uses one environment factor. I need to update also the KD. With that, I have the calculation of the orifice, and if I select, now I change the orifice size to E. If I return to the spreadsheet and consider environment factor as 1 and the KD as 85, now my calculations is 0.15. And we can verify what is the orifice size based on the API standard with the new CPCV. So if I updated this information there, with these 3 updates, I have the new calculation for the orifice that increased a little bit in terms of orifice size, but in terms of relief required, it's increased a lot. In this way, you can see that you will have, based on these results, we can imagine that the differences between the standard API calculation for the orifice will have much more relevance if we consider that our vessel is insulated. If we are talking about a bare vessel without insulation and with the F factor as 1, the calculations, rigorous calculations, at least in this case, and the API calculations in terms of orifice size is almost the same, will lead in this case to the same orifice letter. On the other hand, the calculations of the mass flow required is a lot of differences. It is 3 times what we have verified in the example. So guys, in this video, you have seen what are the main sources of information for pressure relief device calculations, and also you learn how to perform calculations for PSVs for supercritical fluids using the standard API 521 calculations and also rigorous modes, based on the work of Ryan. In the paper of Richard, there are an easier procedure to use the process simulation software to perform the calculations, and I strongly recommend you to read both of papers. The Ryan's paper has 10 pages, the Richard paper has only 4 pages, but there are some misleading calculations. What I mean by that? Who did the table once get the results, once did add the results to the table, do not use the correct information for performing the calculation. The procedure is correct, as we have seen, but when the table was filled, the results was got from the incorrect position. Based on that, let me know what you thought about this video. Was it good for you? Was it interesting for you? It will be beneficial to you in your work as a chemical process engineer. Let me know in the comments, because I will see you soon in the next video. Bye bye.